So we are going to do binomial distribution. What does bi mean? Two. What does nom mean? Two. Number. Okay, what else? Number, term, attribute. Entity. Who knows? So binomial simply means two of something. Well, distribution is simply a table that we create, just like frequency distribution, probability distribution, which is what we will talk about. So a binomial experiment So a binomial experiment is one with n independent trials, where each trial could result in only two outcomes. The key thing to note here is independent trials, in the sense that there shouldn't be any connection between one trial and the other. And each trial could only have two outcomes, and those two outcomes in statistical terminology would be a success, and the opposite of success, which is failure. So those two events are complements of each other. One happens, the other cannot happen. So success or failure is what we can expect at each trial, and we have n independent trials. And also, the probability of success is known. And it is usually denoted by the letter P. So we know that probability with which a success would happen. If that is the case, what is the probability of failure?
50%.
50%.
Because success would be a half and half, right?
You're assuming success would always happen with a 50% probability. That's not the case, it's just P.
1 minus P.
1 minus P, very good. So this would naturally mean and some textbooks refer it to as Q. I'll just call it Q. I don't know what your textbook calls it. 1 minus P, Q, they're all one and the same. And how did we get 1 minus P? As I mentioned earlier, failure is the complement of success, and we know that the probability of an event is related to its complement as 1 minus probability of the original event. examples of binomial experiments. I'll start with one. Suppose I roll a pair six-sided die 10 times, and the object of interest, the success event, is getting a 2. So if I roll a die 10 times and the success event is getting a 2, do I know the probability of success?
1/6.
Yes. Do I know the probability of failure? Which is
1 minus 1.
which is
1 minus 1.
which is
5/6.
5/6. So that is a simple example of a binomial. So it's your turn to give me one.
Where you can get an unsatisfactory or a satisfactory grade.
Okay. How many courses?
Like with one course, like 20 students or something.
Okay. Of course, here P is going to depend on the type of course. So the n independent trials would be 20. In the previous case, the n independent trials was 10. And the probability of success was 1/6, and the probability of failure was 5/6. What should we give as probability? Well, first we've got to identify the success. What should success be, satisfactory or unsatisfactory?
Satisfactory.
I just have to make something up. So, for example, I'll just say let probability of success be 0.7, which simply implies the probability of getting a satisfactory grade is 0.7, 70% chance. The probability of not getting satisfactory grade would be 30%. One more example. So, cars driving to a specific destination where the travel time is 20 minutes and the travel time is not 20 minutes. Let's just say not 20 minutes. So, I'll just call it as probability of travel time is 20 minutes or less. And how many cars do we have? 15. So each car is a trial. And do you believe that they are independent?
Unless they're in traffic with each other.
What?
Nothing,
Let's say that the people are not related at all. People who are driving the cars, are they independent? Yes. The success would be travel time being 20 minutes or less. And the value would simply be that the travel time is greater than 20 minutes. Benton, did you have one?
Well, I was gonna say I don't know, I'll just say 30 people choose one marble in a bag of 10 reds and, I don't know, 20 greens, and the success is the chance of getting a red. Or the success event is getting a red marble.
What's up with you and marbles?
I don't know, marbles are cool, they're spheres. They roll down hills.
Can things other than spheres roll downhill?
Well,
Yeah. I'll push a square down a hill, but it wouldn't roll, it's more tumble. But it would still go down. It would still go down.
that's the individuals who choose a red marble from a bag of 17 red and 13 green marbles. There is a question. What is the success event?
Going away.
Choosing a red marble. Do I know the probability of success?
Yes, you do.
Which is?
If the computer wasn't there, I'd be able to tell you.
17 red and 13 green.
17 over 30.
17 over 30. So do we agree that all of these are binomial experiments? Now, if they are binomial experiments and if you know N and P, then we can model the entire experiment and describe all kinds of probabilities using the distribution that I'm about to write. So I guess I'll start with an example. Okay, so studies conducted to assess dating experiences among FGCE students would collect a sample of 36 students, which I am observing here or observed, and I asked if you had ever been on a date, and 26 out of 36 responded yes. Now, I'm going to use that information and extend it to another group of 36 students. So I randomly select a cohort of 36 students, and I would like to analyze based on the sample that I got here and see how successful they are going to be. Good. Let X be the number of students out of the 36 who could have been, might have been on a date. And we want to assume that the students are unrelated. Why should I put that statement?
To make sure that they're like independent.
We want it to be independent. So could we model this as a binomial distribution?
Yes.
Yes? So what are the trials? What is the trial in this example?
Being on a date and not being on a date.
That's the event of first.
The 36 students.
So each student is a trial, so the trials would be the students. What is the success event?
Being on a date.
Being on a date. I don't for once think that, life isn't successful if you've never been on a date. By all means, when we say success in a binomial experiment, it is simply an event of interest. It could be something extremely negative or morbid. For instance, in clinical trials, if we have to model something using binomial, one may say, okay, we give the drug to 20 people and the probability that a person would cough up blood and die is this percent. What are the chances? 5 out of 10 could have this success, right? In that case, success is a morbid event. So success doesn't mean a positive event at all times. It simply means an event of interest. What are we interested in? Doesn't have to be positive. So we have trials. We have a success event. So N. What is the probability of success?
26, 36.
What is the failure event? Oh, failure probability?
10 of 36.
10.
Yeah.
Oh, I see. I'm looking at this. What are the possible values for x? So keep in mind, x is the number of students out of the 36 who could have been on a date.
From 0 to 36.
0 through 36. So for each value of x, we can actually find the probability. In other words, 0, 1, 2, 3, 4, all the way up to 36. We can answer the question, since the problem is binomial, we can answer the question, well, what is the probability that 0 out of those 36 had a date? We can get a number here. Exact 0 would mean none of them. 1 would mean exactly 1 out of those 36. 2 would mean exactly 2 out of 36, and so forth. Does that make sense? Can't work this problem out manually because it's going to take forever, so I'm going to modify the problem a bit. But when we have this, we have a table, correct? So for each value of x, we have a probability. We've constructed a table with 37 columns and 2 rows. This table is what we call a discrete probability distribution. Why do we call it discrete? Well, the outcomes are discrete. We could simply have a 0, 1, 2, 3, 4, 10. If we can't say 4.5 out of those 36 people, would be on a date. Hence, discrete. The variable x is discrete. Why do we call it a probability distribution? because we're summarizing probabilities for each discrete outcome. Does that make sense? Yes? Okay.
Is this part B?
Yeah. Or, a second part of this problem, because I'm going to go for ABC. The reason why I'm reducing the number here is because it'll be easier for me to write this table out for 5 people. But if it's 36, it's going to take forever. When we do it using a calculator, we can do this easily, but we're not using a calculator yet. What are the possible values for y?
0 through 5.
0 through 5. None of the 5 end up guessing a date, or exactly one of them would, or all 5 of them would, because y measures the number of students out of the 5 who might have been on a date. So our objective is to find that discrete probability distribution. So the name in this case, it is a binomial distribution. Why do we call it a binomial distribution? Because the scenario we consider is binomial, right? We have 5 independent trials now. The probability of success is still getting, or might be on a date, or being on a date. And we know the probability of success, which is 13 over 18. So we have to find or form a table for each possible value of y, 0 through 5. Going to start with the first one, probability that y equals 0. In words, what would that mean? Y equals 0. in words, how would you interpret it?
0 out of 5 students went on a date or have
Okay.
been.
Or in a simple sense, right? So if this probability were to be true, which I got a sample, I extended it to 36, and then I made a comment that the very same probability would hold true for any n. In this case, I'm using n to be 5. And we want to find probability of y equals 0, which means none of the 5 has been on a date. Now, in how many ways could that happen? Or how would you find this probability?
Given that all 5 are failures, you can take the probability that 1 is a failure and raise it to the 5th power.
Okay, so every single one of them failed. So first one is a failure of the Q. The probability of a failure again, Q. The third person failed, the probability Q. Fourth person failed, with probability Q. Fifth person failed with probability Q, right? In other words, I'm saying that the first one failed, and the second one failed, and the third one failed, and the fourth, and the fifth. That would mean all 5 failed. So that would equal to Q raised 5. I want to insert P here, just for fun. So without changing anything algebraically, I need to throw in P somehow. In other words, I need to have a P here. What should its power be?
0.
0. So this is the only way that event could happen. Do you agree? Can you think of any other possibility? No. So, if a particular experiment behaves as in a binomial fashion, then we can formulate this, and at the end, we can say the power of Q would be the number of failures that we would have. The power of P would be the number of successes. And the first term would be the number of ways in which a success could happen. It's not a success for the event y equals 0. In how many ways could y equals 0 happen? 0 successes would simply imply 5 failures. Yes? And vice versa. Now we want to move on to probability of y equals 1. Y equals 1 would mean 1 out of those 5 ended up or has had a date or would likely get a date and so forth. So how many successes would we have?
1.
1. If we have 1 success, how many failures would we have?
4.
4. So what is the power of P?
4. 4. 5.
Why 5, Bailey?
Because the first person could have been on the date and everyone else fails. The second person could have been on the date and the first person as well as everyone that follows fails, and vice versa for all of the spots.
So it could be success, failure, 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 failure. Right? Failure, success, failure, failure, failure. Failure, failure, success, failure, failure. Failure, 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 success, failure. Failure, 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 success. In other words, you know, one outcome is the first person is, the second, or third, the fourth, or the fifth. So that would simply be 5. Two successes would mean how many failures?
3.
3. How many number of ways?
10.
10? How'd you get 10?
Because you have double the factors as you did in the y equals 1.
So your argument is if it were to be 3, we would have 15. And if we have 4, it would be 20.
Yeah, because there's 2 successes and 5 factors, so you just multiply them against each other.
Okay, what else?
Am I wrong? Yeah. Okay, then what's their answer?
10 is correct, but the way you explained it is incorrect. So your answer is, okay, it has to be 10 because it was 5 here, and this is 2 now, so we'd have 10.
No, the number of successes would be 2. P equals 2, right?
Mm-hmm.
There's 5 factors because there's 5 different people, so 5 times 2 is 10.
Okay, so if I had 6, it would be 6 times 2, that would be 12.
What? If you had 6 people? I'm very confused as to what you're asking.
Y equals 3.
Okay.
How many successes would we have? 3. How many failures? 2. What is that?
10.
10? Why?
Because it's the same thing but backwards.
It's the same thing but backwards. So, enlighten us. What's your name?
Lauren?
Lauren, enlighten us. So, Bailey, what would your answer be in this case? You would have said 15.
I would have said 15.
Right, that's what I'm trying to say. It's not 15, it's 10. Enlighten us, Lauren.
Well, it's the same probability because they're the same numbers, they're just backwards. The number of possible failures and success, I mean, there's still 5 people. I don't know how to explain this, so.
You're correct, so I'll just explain it. As long as you get the point, that's all that matters. So going to 2, right, if we write this out, what we would have is, right, that's one possibility. Another possibility would be that. Another would be that, yes? Another would be that. Yes? And I could keep on writing all 10 of them, right? What Lauren suggested is I'm just flipping so it would have the same 10 possibilities. All she implied was replace all the F's by S and S's by F, right? You'd get the same thing, same number of ways. So this would be 10.
That makes sense.
So 4 successes would mean how many failures?
1.
1. What should this be? Bailey's going to say 20.
5.
5. Because the same argument. What happened here, it's just going to happen in reverse because things just switched. So 5. Five successes would mean how many failures?
0.
0. In how many ways could we have 5 successes out of 5 people?
1.
This is great and all. Suppose I want to do this using, well, I want to do it this way, but for n equals 36. The one I wrote earlier, that lengthy table, 36 students, 37 possibilities. How easy do you think this would be?
It would just be time consuming.
It would be time consuming and you'd actually lose your mind, right? And you will become one of these people never getting a date. So, because you'd spend the rest of your life doing F, F, S, S 36 times. So there has to be a better way. Remember last time we had combinations where order didn't matter, right? So we had 5 people and we want to choose the number of people out of those 5 who got a date, in other words, a success. Does the order matter? No. All I care about is success. So it's like saying I've got a bag of 5 students, arbitrarily I pick one as a success. And how many ways could it happen? It could happen in 5 ways. So each of those that you see here this is 5 choose 1. Oh, 0, sorry. That is 5 choose 1. That is 5 choose 2. 5 choose 3. 5 choose 4. And 5 choose 5. Pick up your calculator. I showed you how to find combinations last time. Verify if you get the same numbers. Go ahead, David.
So what would you?
Now, 5. Do the same thing again. 0. P raised 0 is just 1. What is Q? Q is 5 over 18. Raise it to the power of 5.
Could you not just type 1 in the parentheses instead of 5, 0?
We can, but I just wanted to
Okay.
show that it works. So I'm going to become lazy in a bit. 0, 0,
165.
165, let me just call it 17. Round it to 4 decimal places. So you can verify the combinations at home. So I'm just going to go with the values that we have. So second case, 5, 13 over 18 raise, how many?
1,
1.
and then 5 of 18.
Multiply that by 5 over 18. Raise how many?
4.
4. The next one is 10. Multiply by Laura.
I have no idea, I'm lost.
So what I'm doing is I'm evaluating each of those, right?
Mm-hmm.
So I did 1 times p raised 0, 5 over 18 raised 5, because q is 5 over 18.
Okay.
Then I have 5 multiplied by p, which is this line over here,
It's 13 over 18.
13 over 18. I take that answer and I multiply by 5 over 18 raised 4, which is q raised 4. And I'm going to go to the next one. I have 10 multiplied by 13 over 18 squared, multiplied by 5 over 18 cubed. And I'm going to do the same thing for all values.
Thank you.
Question.
Yes,
Since y equals 1 and y equals 2 are, y equals 2 and y equals 3 are the same numbers, would it just be the same outcome?
why don't you try that? Would it be?
Because if you just tell me that I wouldn't have to type it.
No, it won't be.
Okay, cool.
We're doing 2, yes. So I'm evaluating for y equals 2. I get 0.1117. Yes?
I rounded it to 8.
Huh?
Since we rounded all the other numbers, it'd be 8.
And next, all I have to do is change these numbers. Yes. 2. .2907. Plug in the next value. I should just type it a bit faster. You can try the next one instead of us wasting time. And it froze.
3779.
So note each value is a probability, so it has to be between 0 and 1. When I add all of those values, what do I get? 1. Because of rounding, it might come close to 1, 0.99999, but it has to be 1. So a discrete probability distribution has to satisfy the condition that each probability is between 0 and 1. That's a requirement for a probability. And sum of all probabilities must be equal to 1. So whatever we did there and if the way we evaluated the probabilities can be done easily with this function. Second bars, 3ARS. Right next to the clear button. So, this is a distribution and this is binomial. And we are trying to find the probability for each and every value, which simply means y is exactly equal to 0, y is exactly equal to 1, y is exactly equal to 2, and so forth. Anytime we want to find an exact probability, you will have to use a PDF function. Write that note. PDF functions are used for exact probabilities, especially with discrete variables. If I scroll down, option A, you see binomial PDF, right? Now, if you have the newer version of the calculator, when you select it, it is going to ask for trials, X, P, yes?
Mine says it's 0, not A. I don't know if that's the right thing though.
Oh, it's fine, it's correct.
Okay.
Your calculator is actually missing something else. We will get to that later at the end of the semester. So, if you have the newer version, who's got the newer version? What does it say when you select it? It should say trials. Is it P and X or X and P? P and X. If it's the older version, you would simply have to enter, so 5 for trials. P is the success probability, which is 13/18, followed by X. X simply is the value of y in our case, each value of y. So what is the first one? 0.
I did something.
And what did we get?
I did something.
0.00165. Talk to me. I'll have to explain this. So, isn't that close to the value we had before? Yes. Now, repeat the same. Instead of 0, plug in 1. And what should we expect to get?
0.0215.
0.0215. Yes. If I enter 2, what should we expect to get?
0.1118.
0.1118. What did we get over there?
0.1118.
And one more, just to top it off. $2907.